Hello and welcome back to the VFX Universe series. Following our two-part special on the top 10 most bizarre planets in the cosmos, many of you raised a fascinating question: if these celestial bodies are located light-years away, ranging from hundreds and thousands to even billions of light-years from Earth, how on earth do scientists actually find them? How can we determine their distance, size, mass, and chemical composition, or even predict the chaotic conditions on their surfaces, when we haven't even managed to land a human being on our relatively close neighbor, Mars? In today's video, VFX will answer all of those burning questions. Welcome to Universe 66. To address the first mystery, how are these distant worlds actually discovered? Unlike stars, which possess the power to shine with immense brilliance, most planets do not emit their own light. Even when they do reflect or emit a small amount of radiation, that glow is incredibly feeble compared to the overwhelming glare of their parent stars. In practice, it is exceedingly rare for astronomers to spot an exoplanet directly through a conventional telescope in the same way you might observe Saturn or Jupiter from your backyard. Almost all exoplanets that have been imaged directly are newly formed gas giants. These planets are still glowing because they remain intensely hot from their formation, and they are typically situated very far from their host stars, ensuring their faint light isn't completely swallowed by the star's radiance. The vast majority of exoplanets are discovered indirectly, primarily through the subtle dimming of a star when a planet passes directly in front of it. When a planet transits a star, it obstructs a tiny fraction of the star's light, causing a measurable dip in its brightness. Scientists use sophisticated instruments to monitor the luminosity of thousands of stars simultaneously. When they detect a rhythmic, periodic dimming in a specific star, they can confirm the existence of an orbiting exoplanet. This technique is known as the transit method. While it might sound as simple as child's play, the actual drop in a star's brightness during a transit is infinitesimally small. Take our own Sun as an example. If a planet the size of Jupiter were to pass in front of it, the Sun's apparent brightness would only decrease by about 1%. For a planet the size of Earth, that reduction is a staggering 0.001%. Detecting such a minute change requires measurements of extreme precision. On the bright side, the transit method does much more than just prove a planet exists. It allows scientists to unlock a treasure trove of data. By measuring the time interval between these transits, we can calculate the size of the planet's orbit. The orbital size tells us exactly how far the planet is from its star. A smaller orbit indicates the planet is nestled close to its sun, while a larger one suggests a distant, colder world. This distance is a crucial piece of the puzzle because it tells us whether the planet resides within the habitable zone, the Goldilocks region where temperatures are just right for liquid water to exist on the surface. Furthermore, by analyzing the specific depth of the dimming, we can calculate the physical dimensions of the transiting planet. Even more miraculously, we can study the atmosphere of an exoplanet during the transit process. If the planet possesses an atmosphere, a tiny sliver of starlight will filter through those gases as the planet passes by, causing a phenomenon known as light dispersion. Dispersion occurs when the white light emitted by a star is separated into its constituent colors. By analyzing the specific patterns of this dispersion, scientists can deduce the chemical makeup of the atmosphere. From there, they can work backward to understand the composition of the protoplanetary disk from which the planet formed, effectively determining what the planet itself is made of. By combining atmospheric data with the planet's distance and the star's temperature, we can estimate the surface temperature and conclude whether the environment is hospitable to life. According to NASA's statistics as of 2020, over 4,000 exoplanets have been officially confirmed. Among them, nearly 3,200 were discovered using the transit method. Approximately 800 were found using the radial velocity method, while the remaining 200 were identified through 7 other specialized techniques that are too complex to cover in detail in this single video. The second most prevalent technique after the transit method is the radial velocity method, often colloquially referred to as the wobble method. This approach is generally most effective for detecting massive gas giants that orbit very close to their stars, a class of planets known as hot Jupiters. Because a hot Jupiter has significant mass and is positioned so close to its star, its gravitational pull is quite powerful. This gravity causes the star to move in a tiny orbit of its own around a common center of mass. From our perspective far away, the star appears to be wobbling or swaying back and forth. As the star moves toward and away from our telescope's lens, the light it emits undergoes a Doppler shift. You've experienced this with sound. When an ambulance speeds toward you, the sound waves from the siren are compressed, resulting in a higher pitch. As it passes and moves away, the waves are stretched, and the pitch drops. Light behaves in a similar fashion. Light waves are compressed as a star moves toward us, shifting toward the blue end of the spectrum. This is called blue shift. Conversely, as the star moves away, the light waves are stretched, shifting toward the red end, known as redshift. The periodic repetition of these blue and red shifts in a star's light indicates that a massive planet is tugging on it. The more pronounced the shift, the faster the star is wobbling, which proves the orbiting planet has a greater mass. By knowing the mass of the star and the intensity of the wobble caused by the gravitational dance between the two bodies, researchers can calculate the exact mass of the exoplanet. Now, you might be wondering, wait, how do we know the mass of the star in the first place? The mass of an isolated star is often calculated using a phenomenon called gravitational lensing. Imagine you are on Earth observing a galaxy in the deep distance. Between you and that galaxy lies a massive object, like a black hole or a star. Because massive objects warp the fabric of spacetime around them, the light from the distant galaxy is bent as it travels through that warped region. In this scenario, the intermediate object acts as a gravitational lens, magnifying and distorting the image of the galaxy behind it. An observer on Earth will see a distorted, circular image or a halo of light around the lens. By precisely measuring the degree to which the light is bent, scientists can calculate the mass of the object acting as the lens. For binary star systems, where two stars orbit one another, we can measure the orbital size, speed, and period to determine the precise mass of each individual star in the system. But what about distance? How can we possibly know the distance to an exoplanet that is many light-years away? The distance to an exoplanet is essentially the same as the distance to its host star. While a planet might be millions or even billions of kilometers away from its star, that margin of error is negligible when you consider that a single light-year spans 9.46 trillion kilometers. Exoplanets can be located anywhere from a few light-years to a staggering 12.7 billion light-years away. Several methods are used to measure these vast distances, depending on how far the star is from Earth. For stars that are relatively close, within a few thousand light-years, scientists utilize the parallax method. In simple terms, parallax is the apparent shift in the position of a nearby object relative to a distant background when viewed from different vantage points. This is a concept that is very easy to visualize. Hold your thumb out at arm's length. Close your left eye and look at your thumb's position against the background, such as a window or a painting on the wall. Now, switch eyes. Your thumb appears to have jumped to a new position, even though it hasn't actually moved. By replacing your left and right eyes with two different positions of the Earth as it orbits the Sun, and replacing your thumb with the star being observed, we can apply geometric formulas to calculate the exact distance to that star. For stars that are much further away, where the parallax shift is too small to measure, scientists rely on a series of interconnected techniques known as the cosmic distance ladder. This begins with finding standard candles. Standard candles are astronomical objects with a known absolute brightness, such as Cepheid variable stars or Type 1a supernovae. Scientists compare two values, the absolute brightness, how bright the object truly is, and the apparent brightness, how bright it looks from our perspective on Earth. By comparing these two values, they can calculate the distance. The distances to these standard candles serve as the rungs of the ladder, allowing us to measure even greater spans across the universe. Absolute brightness is defined as the luminosity an object would have if it were placed at a standard distance of 10 parsecs, or about 32.6 light-years. Beyond parallax and the cosmic distance ladder, there are several other methods for measuring distance that we will explore in future videos.